Okay.
Yes, there is.
Okay.
It's working. Okay. So thank you very much. So welcome to this webinar on the South Brazil.
Sorry, not yet.
Yes,
not yet.
Not yet.
Yeah. Okay, no, sorry, it is okay. Good.
So we are live transmitting on YouTube. So welcome to this session, distinguished lecture webinar on the solid-state circuits and electron device South Brazilian chapter. I am Juan. There is a new board. I want to just talk about a little bit before our speaker Wladek starts his presentation. Just a general info that it was a new board elected. So I am the vice chair of this chapter. Juan, my name. Sandro Ferreira is the chapter chair. We have also Professor Tiago Weber, which is the chapter secretary, and Professor Paulo Aguirre is our chapter treasurer. So we will continue our webinar series, and then I would like to introduce you Mr. Wladek Grabinski, who will be talking about the IHP OpenPDK initiative, technology, devices, and applications. I will go a little bit on his CV. So Wladek, PhD, it's a semiconductor modeling expert with over 30 years of experience in CMOS, BiCMOS, and RF technologies. He earned his doctorate from the Institute of Electron Technology, Warsaw, 1991. Served as ATH Zurich and EPF Lausanne support and process characterization and compact MOSFET model development, formerly with Motorola FSL in Geneva. He now consults in advanced SPICE modeling, Verilog-A standardization, and low-power analog RF IC applications within the OpenPDK initiative. Wladek authored the compact/SPICE modeling chapter in the Springer Handbook of Semiconductor Devices and has published almost over 70 papers. Has established the SDERC track 3 on SPICE modeling, and also involved in TCP and IEEM, EMD, ETTM, ITRS, SP Micro, Wladek, CISPAT, Mixits, etc. Has mentored APFL EEE student branch, and since 1999, Wladek managed the MOS AK Association workshop. This is a series that promote the open source modeling tools and FOSS IC design. So welcome, Wladek. Can you hear me? Are you okay?
Yes, we are connected.
So the floor is yours. I will turn off my camera. Any issue, technical issue related, we will be keeping track of the presentation. But the floor is yours. Welcome to this webinar series. Thank you very much.
I hope all will go smoothly. First and most important, I would like to thank you, Juan, for this unique opportunity to present all within OpenPDK initiative, really focusing on IHP technology, devices, and application. I'm consulting for IHP, and as Juan was introducing myself, I'm also managing series of MOS AK compact modeling workshops. I will be also referring to these activities for the presentation. We will start with motivation. I guess talent gap, which is growing in our microelectronic domain, is quite issue. We can see this not only in Europe, but internationally. And to solve this issue, we strongly believe that open source, in particular, all the software tools and other platforms in our microelectronics domain, it's a solution. I will refer to FOSS IC initiative in India. Then I will go through complementary OpenPDK initiative, not only in Europe, but in United States, Japan and China. I will highlight the status of IHP OpenPDK technology, and at the very end, I will also refer to a roadmap for open source EDA tools, which we jointly edited with a number of industrial and academic partners. Of course, all what we are doing in OpenPDK domain needs a lot of enlargement, and I will refer to a couple of important contributors and financing institutions supporting our activities. Motivation, I guess this is also the case in the origin. We see our microelectronics domain, semiconductor technology and design depleted. This was already pointed out even before the European Chip Act was announced, and Joe DeBock, Executive VP of IMEC, was arguing to build more talents and skill, not only Europe, but internationally in our domain. This was 2023. Unfortunately, a year later, there was an official statistic published by EU authorities pointing about missing 30,000 engineers, technicians, and designers across the Europe. This gets even worse now. By 2030, internationally, we will be missing 100,000 of engineers. That's worse in Asia Pacific. We believe that all what we are promoting in our open source domain, open source tools, OpenPDK platform is the solution. Even before foreseeing this issue, the FOSS platform started promoting open source tools in semiconductor technology and integrated circuit design. eSIM sub-project introduce younger generation to basic of integrated circuit design, simulation, including PCB design. They even went further. They created huge library of, they call this spoken tutorials, which with short webinars, YouTube video introducing teenagers, students in secondary schools and colleges to microelectronics. They provide huge libraries which are based on open source tools. Quite recently, they include OpenPDKs from SkyWater, Global Foundry, as well IHP. This is a summary of basically what I was referring with two important contacts. If you want to learn more about FOSS initiative, access the spoken tutorials, please follow the email contacts. In United States, they were very first to open PDKs for two foundries, SkyWater and Global Foundry. This was financially supported by Google. And at the very beginning, if Fabless was an interface offering access to open source tools, PDKs, and supporting design. Recently, eFabless collapsed, but there is a new group called Chip Foundry. Continue this work and supporting students, researchers, young designers, accessing to SkyWater and Global Foundry technology through OpenPDKs. It's grows very fast, in particular in China. One student, one chip initiative gets a lot of attention, if we can believe these numbers. They are referring to about 10,000 students already participating in this initiative, designing a circuit, including advanced implementation of RISC processors. They offer all in open source domain through different funding organization and academic groups across the China. Recently, it was at Free Silicon Conference at IHP in Frankfurt or other. They even announced very first OpenPDK of 55 nano-CMOS process in China. This is a breakthrough not only in China, but also internationally. Similar activities are triggered in Japan. They also recognizing importance of accessing open source EDA tools, removing barriers, or accessing different levels of IP, and minimizing cost to access local foundry across Japan. So they are following a similar path. Now trying to replace eFabless with Chip Foundry, interacting with Chip Alliance, still counting on financial support by Google. But the main ultimate goal is to have access to local Japanese foundries to enable OpenPDK access. With Juan, we are discussing for a long time OpenPDK Brazil. This is a great initiative, and I hope with my presentation we can contribute to all what he already created and extend this package of information, adding more tools and additional information, accessing OpenPDK for open source integrated circuit design. I'm consulting for IHP. IHP is a research institution in Frankfurt on Oder. They have well-established infrastructure, different technology platform and services. The clean room is industry quality 8-inch pilot line offering full production from enabling early access as well prototyping for small teams, SME startups, and small design teams. All is based on the reference 130 by CMOS technology with different options going through development, enabling early access for qualification process. They have two paths accessing the technology through multi-project wafers, working with Euro practice in Europe, as well providing themselves OpenPDK access for academic partners. Each slide have a lot of references which you can revisit after my presentation offline. IHP silicon germanium process, it's quite unique. It's a bi-CMOS process, which includes high frequency HBT devices. These devices are bipolar transistors operating up to 450 gigahertz, so almost half a tera on silicon germanium. It's unique process, not only in Europe or Germany, but I guess internationally, providing outstanding performance of HBT devices built on CMOS platform. Of course, all other components like Schottky diodes, antenna, NPN diodes, EDS protection, MOS varactors, MOSFET transistor for digital designs are already implemented there. Again, bottom line or bottom slide, you have all references to all related information. We establish OpenPDK, open source CAD EDA tools for integrated circuit design, but also offering free access to chip manufacturing through OpenPDK multi-project wafer runs. This year we went through 4 tapeouts, and the very last tapeout is coming on mid-September, and this will be only CMOS without silicon germanium HBT extension, but offering quite large area to submit your chips. Please scan the code or follow the link to learn more and understand the submission rules. Okay, it's about 4 weeks, but if you are in the middle of the design process, it's an opportunity to you to submit a tape out your chip and eventually get manufactured quite soon. There's, of course, other option. It's low cost open source multi-project wafer access to the technology. We have additional optional run coming later in November, and for next year 2026 we foreseen 3 more tape outs. If you are working on the chip, just follow the link and submit your chip to eventually reserve the area for manufacturing. Okay, I was referring to these points, and similar to commercial teams, IHP OpenPDK, it's free and open source, available on GitHub. Following the bottom link, you can access all complete database for integrated circuit design. We are providing complete process specification, layout rules, basic analog and digital cells. There is memory SRAM generators. We have all primitives for layout, including MOSFET, HBTs, and passive. We provide reference measurements data. System has been qualified to use open source layout editor, kLayout, with full DRC, design rule checked, and LVS, layout versus schematic verification. All cells are fully parameterized as pi cells for the devices. At schematic level, we provide support for Xschem and Qucs. Additionally, for all who are in analog RF design domain, we are supporting numerical simulation of passive components using OpenEMS tool. This is a top-level abstract view. We are providing front-end and the back-end, including passive components, active elements, and digital block on different levels, including schematic symbols, inputs for numerical simulation, SPICE input decks, and Verilog-A definition, which then leads to complete generation of GDS2 layout within your design. This is a little bit off topic, but all who are study semiconductor technology, TCAD, open source TCAD tools provides the virtual fabrication without accessing a clean room. You can design your semiconductor device, perform numerical simulations, and learn more about the device performance. There are different tools like CIDR, which is numerical simulator part of ngspice. DevSim, it's well maintained 2D semiconductor simulation TCAD tool. Cogenda has also 3D options for here, as an example, you can see 3D representation of basic memory cell. OpenPDK initiative was very quickly adopted by academic partners. Here there is a complete design flow established by Professor Rihanna at Stanford University, where she was introducing students to IC design using open source tools from Xschem, schematic entry, ngspice, spice level simulation, Magic for layout creation, including DRC and LVS complete post layout simulation, which leads to generation of GDS file for complete tape out ready to submit for manufacturing. There are also other courses. Surely if you search internet, you will find even more courses related to OpenPDK and circuit design. I'm strongly recommended to have a close look at all the lectures and courses prepared by Professor Moorman, who is very strong supporter on OpenPDK initiative internationally. If you are digital designer, we have well-established digital design flow based on OpenRoad. There is a layout viewer of a digital IC example, and basically starting with an abstract high-level Verilog of VHDL definition, you go automatically through logic synthesis, flow planning, placement, clock optimization, global routing, down to final layout ready for manufacturing. On this flow, basically there is no need for human interaction or designer interaction. We are providing full support through IHP PDK, but of course there are different alternatives to digital design flow. For example, a team at Sorbonne University in Paris, they have their own set of digital design tools. Just follow the link at the bottom of the page. Our partner, Professor Pretel at JQL in Leeds, supports the open source design and publish number of papers, maintaining also on GitHub repository, which helps you to select the tools and set up complete design flow. Analog RF open source design flow, it's less automatized, but we have all components you need to set up to create your schematic. We recommend Qucs-S, which supports spice level simulation by ngspice and Xyce for layout generation and verification, including DRC and LVS checks. We are supporting kLayout and Magic. If you are analog RF designers, you can benefit using OpenEMS for RF components verifications. Here, I would like to highlight a link to open source tools maintained by Professor Pletter there is a second link on this page where you have you will find not only the tools we are supporting, but all complementary tools maintained as a set of Dockers by Professor Pretel and his team at TU Linz. Qucs, it's a front-end schematic entry, supports ngspice simulation. Here, there is very simple schematic example with single RF transistors. Qucs, it's not only schematic editor, but also has a lot of features for data visualization and analyzing your simulation results. Bottom references give you a pointer to a couple of workshops and tutorials where Qucs was already introduced. We will continue this series of tutorials at upcoming ESDER conference in Munich. So if you by chance in Munich, you are more than welcome to join one of our workshops at the ESDER conference. Okay, this is a couple of other examples from single transistor to basic inverter, but you can imagine working on more advanced schematics with Qucs. I will already mention Xschem and Magic. They are well-established industry quality schematic editor, Xschem, and layout editor, Magic. They are mainly used by teams in US who are working with SkyWater and global foundry technologies and OpenPDKs. In Europe, we are recommending kLayout. It's a tool for not only editing layout, but performing all test and verification, including DRC, LVS, and parasitic extraction. There are a couple of other alternatives, but up to now, they are not validated for IHP OpenPDK, including RF EDA with schematic and layout editors. We can install all the tools directly on your laptop or university machines, but there are also a set of tools available online. If you are young researchers or professor introducing students to circuit design, I would suggest to have a closer look at Silivits. It's an online tool where you can start looking at basic example of MOSFET or bipolar, in this case, inverter layout, going through basic layout task, moving this hair bar across the layout. You can even visualize cross-section and see all the interconnect between device itself or transistor, in this case, in simple inverter, going from layout to SPICE simulation. You can create SPICE input deck, run online simulation, and analyze, in this case, very simple inverter. It's a little bit off topic. We do not support PCB design, but creating your new design, manufacturing chip, at the very end, you will also need to create a PCB board to validate or test your chip. KiCad is one of the best open source PCB design tools with advanced schematic entry and PCB design layout. What is important here, at the background, we have also ngspice for transistor level simulation. With Xspice option, you can also do verification of large digital block before finalizing PCB layout with SkyCAD. I already mentioned OpenEMS. If you are analog RF designer, you can benefit using 3D numerical electromagnetic simulation to analyze all RF components in your layout, interconnect, transmission line, spiral inductors, or even antenna. It provides basic 3D design tool with appropriate meshing to start numerical simulation. Initially, OpenEMS was designed to analyze antenna. There's a couple of examples. You can even find more at the official website of EMS tools. In our case, we integrated OpenEMS with Qucs and kLayout, fully supporting IHP OpenPDK. So creating your circuit, you run ngspice simulation, identify Aleph blocks from layout, creating 3D structure for OpenEMS 3D numerical simulation to validate your circuit, then entering back to Qucs lumped element model of S parameter blocks to finalize simulation of your analog RF circuit. This is yet another example at simulation results of spiral inductors, which are available within our OpenPDK. Again, all the links at the bottom of the page give you pointers to workshop tutorials where we share even more details about OpenEMS numerical simulator. Again, this is off topic, but MEMS or sensor simulations are quite topic. These devices are used for variety of IoT or biomed applications, and even in this domain, you can find a lot of open source tools to run complete electromechanical simulations of MEMS or sensor devices for different applications. Here, there is very simple 3D structure of gyroscope for some IoT applications. I'm sure you agree that compact models or SPICE models are essential elements of high quality libraries available in any PDK, commercial or open source. To introduce SPICE models, we are recommending Verilog-A as the coding standards. Here it's very simple AKV long channel Verilog-A model. It's just one page, complete definition of MOSFET long channel transistor model in Verilog-A. We also release AKV 2.6 and AKV 3 as open source models, and both are available online. Locally, back in the Brazil, ACM team run by Professor Gulup Montoro, they are active, very active in compact modeling, and they are providing advanced compact model for analog simulation, which was already verified for IHP SG13 process. Just follow the links at very bottom. Cryogenic, it's again a little bit off topic, but it's a hot research subject. We did AKV validation, not really going to super low 4 Kelvin temperature, but there is a lot of initial work validating models at for these unique applications. After analyzing your device, creating a Verilog-A code, we have different tools supporting Verilog-A compilation. And for IHP OpenPDK, we selected OpenVAF, which is industry quality, open source Verilog-A compiler, fully integrated with ngspice. There are other tools which are, for example, Xyce are trying to integrate these tools for new model compilation, Verilog model compilation. After compiling model, adding to your target simulator, you as a designer, you will basically see no difference except one extra statement. We are including a dynamic library with Verilog-A model. Here we have just a basic SPICE input deck to simulate Verilog-A model and obtain the transfer characteristics with AKV. Model validation is an important task. We are triggering new project to create a test procedure for open source SPICE model validation. And this work is supported locally by NLNet funding. Of course, there are alternatives to Verilog combination with OpenVAF. There are teams like GNU-CAP are working on their own compiler as well. This is something quite new. We would like to working directly with Juan. We are evaluating MOSFET mismatch matrix, which will eventually be implemented and submitted for manufacturing for upcoming September tape-out. The goal is to create a huge matrix of MOSFET transistors. All what you see, it is very first implementation by Juan, working on his PhD. He delivered a couple of presentations with results he obtains analyzing MOSFET for mismatch in using his block. We want to extend and having up to 64K transistor for matching analysis. Implementing such circuit, collecting data, analyzing short distance matching will be beneficial to all who are using OpenPDK, IHP OpenPDK. Again, measurements, it's quite important task. Creating your circuit, you have to test, measure, validate your chip. There are different options. Of course, this is not chip design using IHP PDK, but I selected very simple 4007 CMOS inverter and use Expotec Labrador test circuit lab. This tiny post-stamp PCB includes the complete set of measurements equipment, including function generator, 2-channel function generator, 2-channel scope, and digital analyzer. Connecting this tiny PCB to your computer, you can analyze response of your circuit. Again, it's a dummy example of inverter, and you can see this patterns, blue and green response of inverter to series of signals. Professor Kinnett and his team, they went further. They created a really huge chip. They call this Mobius. Not only to measure devices, but also having a configurable matrix to build basic analog blocks, not single NOP MOSFET devices, but basic analog circuits and digital matrix in center, configure the circuits, and then connecting external measurements equipment. You can analyze your basic sub-circuit. It's unique test chip, and I would strongly recommend to contact Professor Kinnett. He built a couple of chips, and as far as I was informed, he can share with all others who are willing to use his tool for teaching and the classes. There's a couple of more details with more links, just so you can revisit this offline and eventually connect with Professor Kinnett at Columbia University. So we have OpenPDK. It's industry quality PDK, set of open source tools for analog, RF, and digital design. And all this does not stay in the software part. We have a couple of new implementations and chip design which were completed, manufactured, and successfully tested. Here it's an example of IHP open security hardware model, which was designed with open source tools using IHP OpenPDK, manufactured and successfully tested. Our partners at ETH in Zurich, they are designing relatively large design chips based on RISC-V core. Here there is one of example of RISC-V implementation with 3 million gates. Other more recent has been fully designed with IHP OpenPDK open source tools and manufactured and recently tested by students at ETH in Zurich. We have a couple of references there. The chip design PAL platform was introduced earlier on our Mosaic workshops. I was already referring to Professor Prettel and his team at JQL Q at Linz. He started working with SkyWater and now is porting his designs to IHP OpenPDK, and some of the tools have been chips has been already submitted and manufactured. So we are expecting some measurements results quite soon. This is other example of fully automatically generated analog RF IC with RF components by Professor Prettel students who was using the GDS factory. This is yet another open source tools for layout generation or layout automatizations. And I mentioned already that digital design flow is fully automatized. This is not the case for RF analog RF designs, and we are working with our partners at Infineon in Villach in Austria, who already established a modular analog design flow. They start, of course, with proprietary PDK and commercial EDA tools to automatize all analog design tasks from optimization, schematic rail, entry layout verification, and complete transistor level simulation. They are in process of reintroducing open source PDKs and open source tools for all these tasks. Again, the update will be provided at upcoming SDERC conference or workshop at SDERC conference. So again, if you are in Munich, you are more than welcome to join us to learn more about Mosaic analog design automatization tool. In Europe, we have a couple of other alternatives. I was referring to Sorbonne University. They established Coriolis design flow with the same goal to have fully automatized IC, analog IC design. There are similar tools also available in open source. This is a work of team at Minnesota University when they already apply machine learning and AI for layout optimization. The very first implementation of this project was done with Intel as industrial partner. That's why you have a couple of blocks as proprietary. But they are working to extend this to open source PDKs and open source tools. There are plenty of publication, including books. So if you want to learn, just take one book, and this is which I would strongly recommend, work of Professor Prettel's students, guiding you from code level and all the design chips to fully functional integrated circuit or chip. What next? We strongly convinced that not only IHP, OpenPDK, but OpenPDK initiative is something which enable students, young researchers and designers to continue work in our quite depleted microelectronics domain. The advantage is that using all open source, we do not have closed commercial PDKs, so you do not need any paperwork, administrative task, signing endless NDA documents or restrictive NDA. All is open not only to academic institutions, but also to small commercial teams, SMEs, startups, which can be benefits of having access to basically no cost design flow. Okay, so I already mentioned about eSIM as an outstanding, unique starting point. If you are new to integrated circuit design, just follow the link and learn more about the tools. Google sponsored OpenPDK of SkyWater and Global Foundry were very first to trigger this international initiative. It is followed by Japan, like group called Minimal Fab or OpenSushi. I'm really impressed by Chinese one student, one chip initiative. Is it true that they have thousands or maybe already hundreds of thousands students making IC design? I would wish to have a fraction of the students here in Europe. IHP remains only one institution in Europe offering OpenPDK. I hope we will manage to convince other European foundry to join this initiative. Other groups and associations, including IEEE, Solid State Circuit, and CAS, they are very active. In particular, CAS in your region, Latin America. Just follow these links and you can engage yourself in the process of integrated circuit design using open source tools. For digital designs, we have open source RISC, which dominates digital flow. And yes, links at the bottom gives you access to more information about risk and its implementations. In Europe, all was quite kind of maybe chaotic. It's a wrong expression, but distributed. So with a group of academic and industrial partners, we edited open source EDA roadmap for Europe. This was huge team effort, which led to or help us to identify 3 short-term actions, mainly all activities in open source mixed signal design, productivity, interoperability and verification for European chips, and system of chip innovation. These 3 topics, they led to 3 new European projects, which eventually provide additional financial support in our OpenPDK and open source EDA domain. Again, still this year, quite soon in September, we will have 3 open multi-project wafer run for IHP open source or OpenPDK. So if you have or if you are working or if you are concluding your design, this is an opportunity to manufacture and receive free silicon with your working chip. Alternatively, we are providing low-cost access to multi-project wafers for the same project. We have extra run in November this year and 3 more runs in upcoming year. So if you are working on the chips, just follow a link and eventually reserve silicon area for your design. We at the process of estimating total area, but it strongly depends on amount of the submitted chips and users willing to tape out and eventually manufacture the chips. By this, I'm coming to a conclusion. This is a huge effort to collect all the tools, maintain and further develop, including new enhancement requests. And surely this list, it's only partial. I would like to especially acknowledge René Scholz, who is the OpenPDK project lead at IHP, our partners at ETH Zurich, Linz, also IT Bombay, who were very first introduced FOSS platform. All what we are doing, it's open source, OpenPDK, it's free to download and free to use, but not free to maintain and develop. So we are appreciating financial support of variety German institutions providing financial support. This includes the FMD as well, Federal Ministry of Education and Research. The same applies to the roadmap. It was huge team effort by our academic and industrial partners. And again, I guess this is not complete list of contributors, which leads to a new proposal, and eventually this will be a reference for new European open source PDK, PDK and open source tools projects. By this, I'm concluding my presentation. This year was quite busy. We went through a couple of workshop tutorials and meeting around the globe promoting OpenPDK initiative. Today, I'm more than happy to share all information with you through IEEE-EDS solid state webinar and we will continue this promotion and interaction with open source community at upcoming events in Shenzhen, later in September, Silicon Valley, Munich, eventually end of year, Silicon Valley, and Bangalore in India. So with this, I would like to thank for your attention, and we can eventually have short discussion, and I'm available to answer any of your questions. Again, thank you very much for your attention.
Thank you, Wladek, Grabinski. Very, very interesting talk. You open a new whole world for all the designers and process engineers. So we are open for a Q&A section. Any question you might have, you can put in the YouTube chat. If anyone doesn't have any questions, I will put mine. I will.
Yes, I can say it was
yeah. So how it works in terms of support? We know that commercial EDA tools we pay for their support. How does technical support work in the open source IC design tools, especially when using this OpenPDK from SkyWater, GF, and IHP?
Yes.
To whom we should address our technical issues?
So yes, as I mentioned, we are talking about open source tools, OpenPDK. It's free to download and free to use, but it's not free to maintain. In case of IHP OpenPDK, they establish internal group. This is a small team, I guess 6 engineers, IHP engineers, working between the technology team and OpenPDK, providing technical question, maintaining GitHub repository, looking for all the question enhancement requests, and they are highly professional. We are lucky that open source initiative was recognized in Germany, not only in the land of Brandenburg, where IHP is located, but also at federal level. We have financial support of Ministry of Higher Research and Higher Education in Germany, who are providing funding to support the tool developers. We have direct interaction with team maintaining ngspice in Germany, Qucs in UK, Xschem, I guess the developer is in Italy, kLayout, it's also local German open source enthusiast maintaining this tool. So through this channel, we are providing some financial support. All the tools are mainly available on GitHub. GitHub is also the main communication point. If you have any issue, problems with installation, maintaining tool, integrating, complete flow, schematic entry, layout, accessing all complementary tools like OpenEMS, submit your question or enhancement request or any other comments or queries through corresponding GitHub repository. The response time, surprisingly, is very fast. So you are not waiting on the phone for hours, and I cannot guarantee 24-hour response, but they are very fast.
Okay, we have time for one more question, Professor Sandro.
Yes,
it's asking. So, what are your expectations in terms of OpenPDK tapeouts for, let's say, in the coming years? Are you seeing this movement like increasing? We will see a lot of silicon coming from that.
So, what I'm saying, it's more from IHP point of view. This year we supported tapeouts and offering free silicon mainly for our academic partners. next year, we are hoping that European project will provide additional funding. So to a certain extent, we can keep some tape outs, multi-project wafer runs free. But bottom line is money. So there is this alternative option where we're trying to minimize the manufacturing cost, offering low-cost IC production. In long term, we would wish to have more, not only academic team, but also commercial, small startup SMEs submitting larger projects or chips. Then having larger volume, we can minimize cost even further.
Okay.
And we are in progress. We have open discussion with local European foundries. It's tough talks, and if other will join, we will have also eventually access to other foundries joining OpenPDK initiative and having alternative foundries supporting open source IC manufacturing. But it's yes,
it's a growing movement.
Yes, it's still some progress. As you can see, with such partners as Google, they managed to have OpenPDKs in United States. In Germany, IHP was very first, or still is very first, with financial support was federal institutions. This was recognized in China, and they have their own OpenPDK, and Japan is coming. So if
maybe Brazil in the future, who knows?
You as designers, they are more than welcome to submit your chip for IHP manufacturing. Of course, you have alternative path with SkyWater and Global Founder in United States.
Okay, so there's no more questions. I think we can end the presentation. Well, thank you very much, Wladek, for this opportunity and for all the efforts for making this very clear and beautiful presentation. And see you in the next live event. And thank you very much.
I appreciate the invitation, and of course I will share my slides so you can distribute locally. Each slide has all the pointer references, so our audience can review this offline afterwards. So.
Okay. Thank you very much, and
thank you very much. Have a great day, and see you next time. All the best. Bye for now. Okay. Thanks for your invitation.
Okay. Bye-bye.